Now we have to do rotation about fixed axis, rotation of rigid body about fixed axis. So, and that's also called pure rotation. That's also called pure rotation, right? See, a rigid body undergoing a pure rotation, I can describe the dynamics of rigid body using Newton's second law that holds for rotation, that is, torque acting on the rigid body about any point is equal to moment of inertia of the rigid body, torque acting on the rigid body about certain axis equals to the moment of inertia about that axis into the angular acceleration of the rigid body about the same axis. So they all are referred to certain axis. Here torque is, this is torque, tau is torque, I is moment of inertia, and alpha is angular acceleration. Alpha is angular acceleration, right? This is angular acceleration. Okay. So let me take an example. Let me take an example of this pure rotation. This is rotation over a fixed axis. For example, say if suppose I have a pulley mass system. Let us take an example of pulley mass system. The example is all about, it's you have a pulley over here, and on the pulley you have the string. This is a pulley mass system. You have mass M1 and M2. Suppose M2 is greater than M1, and here the pulley is having a radius of R, and say the moment of inertia is I, or the mass is M, you can say, right? So this is the pulley mass system. Yes, not light pulley. Earlier in particle dynamics, I took the pulley to be light, but pulley here is not light. It is having some mass, and it's not frictionless. The pulley is not frictionless. The string does not slip over the pulley. Here the string does not slip over the pulley. The string is not slipping over the pulley. A string is moving along with the pulley. There is no slipping between a string and the pulley, right? So in this case, first thing we have to do is we have to draw, of course, the free body diagram, right? We have to draw a free body diagram. See, what's the difference between in dynamics? If you remember, I talked about light frictionless pulley in the first chapter. I think the first chapter I talked about light frictionless pulley, but here the pulley is having some mass. Pulley is not light and frictionless. Pulley is not, it's not light frictionless pulley. Pulley has got the mass, and there is a friction. Here in this case the string slided over the pulley. String was slipping over the pulley, but here string is not slipping over the pulley. See, if there is no friction between the pulley, suppose this is your pulley, and say this is the string. Say, let's call this a string, right? The string is like this. This is the pulley. Say if M2 is greater than M1, then when the system is released, this string will have tendency to move in this direction, and this string has tendency to move up, right? This string has tendency to move in downward direction. This string will go up. This string is going up. So in absence of any friction, or when M2 is greater than M1, this string will try to slip over the pulley, and if there is no friction, the string will continue to slip and see, if there is friction, it will oppose, but if there is no friction, string will be slipping over the pulley. But if there is friction, then the static friction will first act, it will oppose, it will act on the string in direction opposite to the direction in which you have the tendency of relative motion. See, when M2 is greater than M1, M2 greater than M1 creates a tendency in the string to move in this direction, in the clockwise direction, right? But if there is a friction between string and the pulley will exert a friction force in this direction. Pulley will exert a friction force in this direction. Getting a point? Pulley is going to exert a friction force along the string in opposite direction, and as a reaction, the string is going to exert a force on the pulley in opposite direction. String is going to exert a force on the pulley in opposite direction. F will act in opposite direction, right? And what the friction is doing? This friction will make the pulley rotate, and it will rotate in such a way, this friction, it's not like string won't move in this direction. String will move, but pulley will also move. The string will move in this direction, but simultaneously pulley will also move, and every point on the string which was in contact with the pulley, there won't be any relative motion. If suppose you have point P on the pulley and point P dash on the string, and they are in contact, so they will remain in contact. They were in contact from here, they will remain in contact. So this pulley is also moving, and along with this pulley, string is also moving. As the pulley moves, this side the string is wound up, and here the string is getting unwound. There is no slipping over here. There is no slipping between string and the pulley. What happens is, as the pulley moves, say pulley moves by an angle of theta. If pulley moves by an angle of theta, then r theta length of the string is wound up this side, and r theta length of the spring open up this side. R theta length of the string gets wound up this side, and r theta length of the string gets unwound this side. On this side, this mass is going to move up by a distance which is given by x equal to r theta, and on this side, this mass is going to go down by a distance x equal to r theta, because from this side, r theta amount of the string is getting unwound. R theta length of the string is getting unwound from this side, and r theta length of the string is getting wound up this side. Getting a point? There is no slipping as such. There is no slipping as such. The string and the pulley moves together, right? As this P and P dash come in contact, it remain in contact till this point, and then P goes this way and P dash goes this way. Getting a point or not? So this is how, in this case, string is moving. String is not slipping over the pulley. String is moving along with the pulley. So this friction is leading, this friction is making the pulley rotate. This friction is making the pulley rotate in a clockwise direction. If M2 is greater than M1. And not just this. This friction will lead to difference in the tension on both sides. T1 on this side and T2 on this side is going to be different. And what's the difference? Difference is equal to the friction force acting on the string. The difference is equal to the friction force acting on the string. Like if suppose I give you a simple example over here. Suppose you have a person over here and you have a person over here, and suppose they are holding a string and they are playing tug of war. They are playing tug of war, right? They are playing tug of war. They are pulling the string towards themselves. So you have the tension in the string. That tension is going to be same throughout. That tension is going to be same throughout. But if suppose a person, suppose this is A and B, the tension in the whole string from A to B is going to be same. But if suppose a person comes over here and he start pulling the string in this direction, he start pulling the string in this direction, and let's say this is C, then what will happen? Can you still say that tension in every part of the string is going to be same? It's not. Tension in AC and tension in BC segment is going to be different. In fact, tension in this segment is going to increase and tension in this segment AC is going to fall. Tension in the segment BC is going to increase and tension in the segment AC is going to fall. In fact, tension over here T1 will be less than T2. In the same way, on this side the string is pulled by this M2 and on this side string is pulled by M1, right? So if there is no force acting in between, the tension throughout will remain same. But if there is a force F acting on the string in this direction, so tension this side is going to increase. If this is T2, this is T1, tension on the M2 side is going to increase, tension on this side is going to fall, and difference in tension is equal to total friction force acting on the string. So now I can draw the free body diagram. This is tension T1 and you have M1G, then you have T2 and you have M2G, and on the pulley you have T1 and T2. Here it is fixed, rotation about fixed axis, the axle is fixed, so it's free to only rotate. Okay, so suppose M2 is accelerating downward with A, M1 accelerating upward direction with A, and the pulley is undergoing an angular acceleration alpha. So what's the relation between A and alpha? See, if this is moving by x, this is moves by theta, and the relation is x equal to r theta. See, if I take the derivative, what will happen? X dot equal to r theta dot. I take double derivative, x double dot equals to r theta double dot, and x double dot is what? A, and theta double dot is alpha. So A equals to r alpha. Okay. So if I apply Newton's second law, this is T1 minus M1G equals to M2A. This is M2G minus T2 equals to M2A, and the torque developed by T2 is T2 into R on this side, and torque developed by T1 is on this side, so it is T1 into R, and that's I alpha. That's going to be I alpha. So this is 1, this is 2, and this is 3. So this third equation can be written as alpha can be written as A by R, and R will come from this side, so it will be I A by R square. This is third, and what you can do is you add 1, 2 and 3, so I will be getting M2 minus M1G equals to M1 plus M2 I plus R I by R square A, and A is I upon R square. This is the acceleration. This is the acceleration. Okay, this is how. So this is the spring pulley mass system. This is very important, pure rotation. Pulley undergoes a pure rotation. The axis is fixed. The pulley is undergoing a pure rotation in this case. Okay. Now let's move to next question. See this question. The wheel of radius r and moment of inertia I about its axis is fixed at the top of inclined plane of inclination theta as shown in figure. A string is wrapped round the wheel and its free end supports a block of mass m. The string is wrapped round the wheel and its free end supports a block of mass m, which can slide on the plane. Initially, the wheel is rotating at a speed omega in the direction such that block slides up the plane. How far will block move before stopping? Let's see this question. So first of all, let's draw the free body diagram of both the body. See, this is the block, mass M. So the forces acting on it are, one force is mg, other is normal reaction, and this is tension. And on the pulley, the only force which is going to create a torque is T. The force acting on the pivot, the center axle, is not going to create any torque, because that is the force passing through the center. So force acted upon by this axle or pivot is not going to create torque. This force is going to create a torque, and when this force creates a torque, it's going to accelerate the body in this direction. It's going to accelerate the body in this direction. Getting your point? The acceleration produced is going to be this. See, one thing I should tell you, that the acceleration and the velocity need not be in same direction. The acceleration and the velocity need not be in same direction. Like when you are riding a vehicle and you come near your home, then you pull the brake. Then you pull the brake. And when you pull the brake, you are accelerating towards, you are moving towards your home, but you are accelerating in opposite direction, because velocity is falling. Velocity is falling. You are moving towards your home, but you are accelerating in direction away from your home, right? So the acceleration and velocity need not be in same direction. Here the wheel is moving in this direction, but it's going to accelerate in anti-clockwise direction. Wheel is moving in clockwise direction, but it's going to accelerate in anti-clockwise direction. It means the magnitude of angular velocity is going to fall, and it will finally fall to 0. So if direction of angular acceleration is this, the direction of linear acceleration of this mass will be in this direction. There has to be matched. Like if your pulley rotate in this direction by an angle theta, then the string which is unwind is r theta. So this is going to move in this direction, right? If pulley moves in this direction, this mass moves in downward direction. Say pulley accelerates in this direction. If the angular acceleration of the pulley is in anti-clockwise direction, then the linear acceleration of the mass will be towards downward direction. There has to be a match. If pulley is moving in this direction, the mass will go up in this direction. So there has to be a match between omega and v. There has to be a match between x and theta. There must, direction of a and alpha should also match, right? So if alpha is in anti-clockwise direction, a will be towards downward direction. So it means what? It means if omega is falling, this velocity is also falling. If omega is in this direction, velocity will be in upward direction. So as omega falls, v will also fall. A time will come when omega will become 0, and this mass will come at rest. And thereafter, this mass will start falling in downward direction. Initially, your omega is in this direction, v is in this direction. Pulley undergo an acceleration opposite direction. It will lead to fall in omega. It will lead to fall in omega. So it will lead to fall in v also. Acceleration will be in this direction. The v will also fall. A time will come when omega will fall to 0 and v will fall to 0. Omega will fall to 0 and therefore v will also fall to 0. In fact, the relation between the angle moved by this and distance moved by this is this. And the derivative gives you x dot gives you r theta dot, right? And x dot is r theta dot. So you have v equal to r omega, and if I take derivative once more, I'll be having a equals to r alpha, right? A equals to r alpha. Okay. So this is how the direction of v and omega, r and theta, x and theta, and a and alpha must match together, right? Now let me apply the Newton's second law. See here, your TR is I alpha, and on this side, if I put a axis in this direction, say I'll put a red pen over here. So this is your x and this is a y. Then in that case there is no net motion in y direction. There is no motion in y direction. So n minus mg cos theta is going to be 0, and mg sin theta minus t is ma, right? And your TR is I alpha, and the relation, the fixed, this is rotation of fixed axis. If it moves by theta, then r theta amount of string will wound up, unwind. This will move by r theta. So this is the relation you have, as we discussed in last question. This is, if I put alpha, A is r alpha. So if I put alpha as A by r, so T will be IA by r square. So this is A, this is 1, this is 2. You add 1 and 2, you will be getting mg sin theta equals to what's the B is M, capital M. So I think here also it will be capital M, and here also it's going to be capital M. So it's M plus I upon r square A, and A is mg sin alpha upon mg sin theta upon I upon r square. Okay, so the distance covered is going to be given by this relation. V square is omega square r square. In the beginning V was omega square r square, and this is going to be 2mg sin theta upon, okay, this is going to be distance traveled till mass comes to at rest. Mass comes at rest. So we can do this problem. This is also example of rotation about fixed axis. Alright. Now let me move to one more question. See this question. A man of mass m1 moves on the periphery of disk of mass m2. There is no slipping involved. If man starts from rest, find the angle moved by the disk in a space when man reaches his starting position. This is a very interesting question. Let me discuss with you. Suppose this is a disk, right? This is going to be the disk. Say this is a reference from where I'll measure the angle. This is a reference which is fixed in space. Man was here in the beginning. As he starts moving in this direction, he'll be pushing the disk with a force F. Is going to push the disk with force F, and disk is going to push the man with force F. As a result of which, the man is going to accelerate and disk is going to accelerate in opposite direction. There will be an angular acceleration, that is I into alpha. If suppose the man is here at t, say at time t, the angle moved by the man is theta. See, when he start moving, he'll mark a point P over here. As a man moves in this direction, this will move in opposite direction. I have drawn this line in space. It's not line of disk, it's line in space with respect to which I'll imagine this theta. So the man is moving along the periphery in this direction. So when man covers the angular distance of theta, suppose the disk moves by an angle of say phi. Disk will move by an angle of phi in opposite direction, right? They were together over here. Suppose the point P is the point P from where it started. This point P was here, man was also here. this point P at time t at t equal to 0, point P and the man were at the same point at this position. But as a man moves in this direction, the point P is going to move in this direction, right? Point P is going to be moving in this direction. Suppose man has covered an angular distance of theta, point P has covered an angular distance of phi, right? So the distance covered by man is going to be r theta. So the acceleration of the man will be what? Second derivative of this distance, that is r theta double dot, right? Whereas alpha is phi double dot. Point P was on the disk at t equal to 0 was here, and man was also here. Now the disk is moving by an angle of phi. So from here, this r and this r will cancel out. So from here we get an idea, m1r theta double dot is half m2r phi double dot. So m1 theta double dot or twice m1 theta double dot is m2 phi double dot. And in that case, if I integrate on both sides with respect to time, this is going to have plus constant. Initially, the velocity of man is r theta dot, and velocity of the disk, that is theta phi dot, both are 0 at t equal to 0. So theta dot and phi dot both are 0 at t equal to 0. So that will lead to c equal to 0. So you have m theta dot equals to phi dot. Okay. Now if I integrate it once more, then you have m2 phi plus constant. And at t equal to 0, point P was here, man was also here. So at t equal to 0, your theta and phi both are 0. So that will also lead to c equal to 0. So you have 2 m1 theta and m2 phi. So angle moved by the man and angle moved by the disk is sharing this relation. Now, when man reaches the starting position is point P. A time will come when man moving this direction, point P moving this direction, man will again reach point P. Man may reach again point P. Suppose man reaches this position and the point P is also at this position. By that time, suppose the angle moved by the man is theta and angle moved by the disk is phi. So they will continue to share this relation, but then at that time this theta plus phi, this theta and this phi will be what? It will be 2 pi. This is 1, this is 2. Now I can simply solve this. I can just put phi equals to, you have to find out what? Angle moved by the disk. Okay. So you just put phi equals to, theta will be, phi is, sorry, angle moved by the disk. Okay. So theta is m2 phi by 2m1. So you put it over here, says m2 phi by 2m1 plus phi equals to 2 pi, and that becomes (4m1 pi), or phi is 4m1 pi plus m2 plus 2m1. Okay, that's going to be our answer. So this is how we go for the problem in case of rotation or fixed axis.